20 naturally occurring amino acids, alpha amino acids for that matter. These are the ones that are used to build proteins. Okay. And now another, I guess it's next week that you need to know all of the 20 amino acid structures, their one-letter code, three-letter codes, and names. So now we're going to start talking about the ones that are polar, okay? Those that are polar at, these are just ones that are polar, predominantly at pH 7. Once again, we have some that can follow, that can kind of fall between multiple categories. We have the aliphatic, which then we can also talk about ones that are aromatic, like tyrosine, tryptophan, histidine, which you haven't seen yet, and tyrosine, tryptophan, histidine, phenylalanine. Okay, but these are the ones that are polar, that they aren't necessarily acidic per se or basic in that sense. So we have the two that are very closely related, asparagine and glutamine. Okay, and I actually usually like to talk about the acids, the acid forms first, but the way that this was set up, they talk about the amide forms first. The only difference between asparagine and glutamine are the number of linking carbons between the C alpha, because the C alpha would be right here or right here. Asparagine only has one and glutamine has two. Okay, otherwise it's that and an amide. And so, rather than to draw them both out, I'm just going to draw one of them all the way out. Come on now. So you have a carboxylic acid, and which technically would be a carboxylate. You have your amino.
Is this one asparagus?
Pardon?
Asparagine? Is that found in asparagus?
Well, yes. But, I mean, there are lots of all the amino acids to be found in asparagus. I've had people ask that before, too. I mean, technically, there is asparagine in asparagus, yes. And the same thing with aspartate. All right. And so, asparagine, it has one linking carbon and then the simplest amide. It's supposed to be NH2. And please notice that the amide is not charged on either of these, because under neutral pH it wouldn't be. Okay. So that's why these are not considered positively charged. And I point that out because we're going to see a couple of nitrogens later on that are positively charged, but not on asparagine and glutamine. And the only difference between the two, once again, is glutamine would have an extra carbon here. It has two linking carbons instead of one. Okay. And you're going to find out the exact same thing with aspartate versus glutamate, or aspartic acid and glutamic acid. Notice that the one-letter codes and three-letter codes may not make sense. And that's why I usually like to start off with the carboxylic acids, because glutamine is GLN, and so people want to say GLU, but that's glutamate. Okay, so the carboxylic acid version comes first. But if you think back to Gen Chem, remember the amide is considered a derivative of carboxylic acid. So glutamate is GLU, glutamine is GLN. We'll get to glutamate later, but the one-letter code for glutamine is Q, because it can't be G, because that was glycine. Okay. And you're going to find out it can't be L, because L is leucine. There isn't a U. And it can't be T, because we haven't learned T yet. Well, T is up there, and so that's threonine. And so we can see that they work their way down. And glutamine just doesn't fit in the mold, and so therefore it's actually Q. Right? That's like one of the only ones. I can't think of anything. With tryptophan, the bottom of it made a W, and so you can say it's tryptophan. This one, you just have to memorize. I don't have anything. And asparagine is ASN, and its one-letter code is N.
Is there anything significant about it?
Not really. I mean, it's able to form hydrogen bonding, but it's not like well, say the carboxylic acid ones, or like the asparagine, not asparagine, like alanine and some of these. I mean, they're all unique in God's eyes, right? Faith integration there. But I can't think of anything specifically that and only those two do.
Do we have to be specific with like the amine group, like NH3 or NH? Like, is there? Will it always be like that?
What? NH3 versus NH2?
Yeah.
For the ones that are terminal, you would. Just like you would not put an NH3 on the amide part, because that's just wrong. It has too many bonds. It just doesn't exist. But on the backbone, it can be NH2 or NH3. Under a normal, if it's loose in the body, physiological conditions, it's NH3 plus. Right. Then we have serine. We have the two alcohols. Technically, there are three. Some books include tyrosine right here as well. Like I said, it can fit in multiple things. Tyrosine fits in lots of things. We're going to find out it's an acid. It fits as an alcohol, and it fits as an aromatic. And so this is from the old book, this figure was, and so the old book didn't include it in this section. Serine, the R group, so if this is the backbone, the R group is really easy. It looks like alanine, but it has an alcohol hanging off. Okay? And it's one letter code and three letter code make perfectly logical sense. SER and S. Whereas threonine, which it's one letter code and three letter code, also makes sense, THR and T. But threonine kind of tricks people out sometimes because it's got two carbons and the alcohol's hanging off of the first one. So it looks like that. Okay, or you could have it where I didn't have the alcohol pointing down because of space. But threonine does, first of all, threonine's special in the sense. It's kind of like leucine. What was so special? I'm sorry, it's kind of like isoleucine. What's so special about isoleucine? It had two chiral centers, and so does threonine. It's the other one that's got two chiral centers. It has the normal one from the C alpha, but the C beta, once again, because it has an alcohol hanging off. So it's also got two chiral centers. Serine is extraordinarily special. Well, so is threonine, because both of these are alcohols, but serine even more so than threonine. If you think back to organic chemistry, we talked a little bit about it in one and a lot now too, but what's special about alcohols? What can they do? What are they good at? They are good. Well, not in this instance. Instead of being good leaving groups, they would be good at attacking. They're good nucleophiles. So we're going to find out there are lots of enzymes that utilize serine as the nucleophile. Threonine to a lower extent just because of the fact that it's a branch is a little bit more tricky. But serine a lot of times. And in vivo, inside enzymes, and when you start writing your enzyme papers, don't be surprised if you find out that it's an alkoxide. Because a lot of times think that hydrogen can come off inside an enzyme to where it can be an even better nucleophile. Okay. And so serines are nucleophiles. In fact, all of the serine proteases, they're called serine proteases because it's the serine that's the nucleophile. So in vivo, we utilize it a lot.
So the threonine in the R group is the carbon with the alcohol and the methyl group hanging off of it?
Mm-hmm.
Okay.
Yeah, it's this one right here. You could have drawn the alcohol coming down like this. I just didn't because of the fact that it was so close to the other one drawn. Otherwise, there's no reason why I had it that way. Okay. Well, you can look at the ball and stick and the other methods of showing. Now I want to go to those that are the acids. I'm actually going to start with tyrosine since we've talked a lot about tyrosine. Tyrosine looks just like phenylalanine, but it's got that p-hydroxy group. And so otherwise it's identical to phenylalanine. Remember, this was phenylalanine. It had one carbon, and then it had a benzene ring. Which that did not come out very well. Benzene ring. And then 1, 2, 3, 4, 5. That is like the worst benzene ring that I've ever drawn, probably. But then we just have that P, in the P position, we have an alcohol hanging off. And so, just like serine, Tyrosine is an amazing nucleophile many times, and it can do hydrogen bonding, and it has that polar end group at least, like many things. And it also has the special properties as being aromatic, similar to phenylalanine and tryptophan, and one that we haven't gotten to yet. And if you think back, we covered this in organic chemistry too. I mean, that's a phenol, right? That's a phenol group. And phenols are actually more acidic than what you'd expect because they can form what's called phenoxides, and that's why tyrosine is a really good nucleophile as well. It can be an O- on that end. It's a phenoxide. Okay, so besides tyrosine, I'm going to next talk about cysteine. Now, usually I don't take off for spelling as long as I can make out what you're trying to say. Oh, whoops, I did the wrong one. There we go. This is cysteine. This is one of the only exceptions to the spelling rule. Do not forget to put the E on the inside. Because sometimes people spell cysteine and they forget that E on the inside and it becomes cysteine. And cysteine is something different. So this is one of the few times. Like if you spelled aspartic acid, A-S-P-E-R-T-I-C, something like that, I could figure out what you were trying to say. But you can't do cysteine. A cysteine is when two cysteines come together to form form a disulfide bond. That's called a cysteine. So that's different, has different chemical properties than cysteine. But otherwise, cysteine makes sense. It's CYS and C. Oh, I forgot to point out tyrosine was TYR and Y, the letter Y. Why? Because we love you, kind of thing. But it should make sense. It can't be T because T is already, what amino acid is T? Was what? Threonine, right? And so it's Y, tyrosine. But cysteine is C and CYS. Cysteine is very, very special too because it's also a great nucleophile. Remember, sulfurs are even better nucleophiles than oxygens. They're even better leaving groups. And so there are a lot of reactions that utilize the cysteine for reversible, for a lot of enzymes do because their reversible reactions are quite similar. And are quite easy. And I've already alluded to this fact. So this is what it normally looks like. Come on now, go down. So I have a sulfur and H, so that's a thiol. But remember, thiols are really great at losing their hydrogens to become thiolates, which are negatively charged. But another thing that the thiols can do, or that cysteine in particular can do, is this is when it becomes cysteine. And it forms disulfide bonds. Okay, and so that's why this is used a lot of times for protein interactions. Can help with protein folding. Your body actually utilizes this to also protect itself. Because you can imagine proteins coming off the ribosome where they're being made. It's called the nascent, because nascent means just giving birth. It's just being birthed by the ribosome. It's called the nascent polypeptide chain. But they're a hydrophobic. As it comes through, there are hydrophobic amino acids, and there's hydrophilic ones and everything like that. But the environment of the cell, is it hydrophobic or is it hydrophilic? Hydrophilic, it's full of water. And so what happens is it immediately starts to collapse. And we'll talk about that actually next chapter in greater detail. You have to be careful with cysteine because they may or may not like it. And if there are two of them together, they may hook up and form a disulfide bond where you don't want them. And so your body actually has a tripeptide called glutathione. And glutathione is actually used. It's got a free sulfur, but it's tiny. This has got a free sulfur that comes in, and it reacts with cysteines that you don't want them to react with other things. And so in that way, you can help fold and get everything just right. Then the glutathione can come off. So it comes on and off, on and off. And your body also utilizes it as a pH buffer. Now we have the two carboxylic acid ones. Like I said, we've already learned about asparagine and glutamine. Normally, if I was writing this, I would put aspartic acid, which is also called aspartate. Remember, if a carboxylic acid loses its hydrogen, it's called ate instead. And glutamic acid just becomes glutamate. And in vivo, many times, they end in the ATE. So, for example, monosodium glutamate is more commonly called, what does it go by? MSG. Good stuff for you. All right, and so, but that is, that's what's to do with. Does anyone know why is MSG bad? I mean, it's bad for a couple reasons, but that's one reason why MSG is bad. And some people actually have really hard problems digesting it. First of all, where is MSG? It can, but what food group in particular is known for MSGs? In fact, they used to deliberately put it in. Does anyone know, historically speaking? You can some pastas. Chinese food. They used to, like everything, they just thought, just dump it in there. And I guess back in the old days, they used to even think that it was a better equivalent than sodium chloride for salt and everything, but no, you have to, because we're going to find out glutamate is actually a neurotransmitter. You can like overexpose your body to it and everything. Like I said, some people have a lot of problems. Plus, just the sodium alone isn't. But yeah, a lot of salty foods tended to use. I could have that in there. Okay, but we have the two carboxylic acids, and the only difference between aspartate and glutamate, once again, is the number of linking carbons. If there's only one carbon between the C alpha and the carboxylic acid, it's aspartate. If there are two, it's glutamate. So that's why technically I couldn't fix this table. If you guys were doing this, I'd probably take off like a quarter of a point or something, because they have aspartic acid, but they drew aspartate. Glutamic acid, glutamate. Because the only difference is for it to be the acid, they have to have that hydrogen where it's got the O minus. It's got to have an OH instead, but it's kind of nitpicky. But aspartate is ASP, glutamate is GLU, so both of those make sense. But their one-letter codes do not necessarily, because it can't be an A, because one amino acid is A, alanine. It can't be an S, because one amino acid is S. Serine, and P is proline, and so on and so forth. So it's D. Okay. And then glutamate is E, which that one a lot of people can remember, because GLUE, glue. And so, but I don't know, asp just doesn't go, doesn't have that flow. So you just have to remember. There are certain, and by the way, there are some letters that either have different meanings, like B and another one's slipping my mind. Well, technically O I usually use a lot of times for ornithine, which isn't one. But B means when they can't tell the difference between aspartate and glutamate. Sometimes when you do it working with proteins, you can't tell if it's one or the other, so they give the letter B, as in Bob. And then the other one, is it X, when they can't tell between... I'm saying, no, you can tell between aspartate and asparagine. They call it a B. And I think it's X is whenever they call it, when you can't tell between the glutamine and glutamate. But I wouldn't ask you that part on there. But that's why B and X, you don't see them in the one-letter codes.
Are we going to draw you said the only difference was...
Oh, the one that, here, I'll draw them real quick. They've got it drawn out there, but I don't like that very well. If that was the backbone, because I get tired of drawing the backbone every single time, aspartate has one carbon, and then the carboxylic acid. So now I'm drawing this one. This is aspartic acid. Of course, if it's got the O minus, it's aspartate. Whereas glutamate looks just the same, but it's got one carbon, two carbons, then the carboxylic acid. This time I'll actually draw it like glutamate. So
why do they have it written like that up there?
Pardon?
Why do they have it written like that up there? The O minus.
Because both of those are acceptable, and your body has it both ways. Okay. It's just depending on at pH 7, if it's free aspartate. I mean, if this is aspartate, like that amino acid free at pH 7, it's going to be the aspartate form, not aspartic acid. Your body in different places will have it both ways. Okay. So that's why it says the predominant form at pH 7. I would have to get, those are the carboxylic acids, acid lose your hydrogens, but I could give you the pKa's as well before I ask you that kind of question. All right. Finally, we have those that are the bases. We got our last, which I hate the way they have histidine drawn. I'll show you the way that I remember it. I think it's easier. But we got the last of our aromatics, which is histidine. So the aromatics are phenylalanine, which is the benzene ring, tyrosine, which has the benzene ring, tryptophan, which has that weird-looking benzene ring with the heteroatom cyclic group with a nitrogen next to it. And then we have histidine. Histidine, what functional group is histidine? It's one of the ones you're supposed to memorize. What's that functional group? It's in the imidazole. That's one of the reasons why you have to memorize imidazole. Okay, so I'm going to do histidine first. This is the way that I remember histidine. Once again, we're going back to the good old baseball. Draw your home plate. But now, for your home plate, instead of the nitrogen being at the point, it's on the two sides. Whereas, remember, the tryptophan, it was down at the bottom. And you have to put in double bonds. There's a double bond. It doesn't matter which of the nitrogens you put it towards. And then the two carbons have a double bond. And then there's a linking carbon. Then it would go on up, and that would be, for example, C alpha. I'm going to go ahead and draw it all the way out this time because it's kind of tricky. And there's the amino group. So just don't forget the linking carbon, but I just always remember home plate with the two nitrogens on the side. You just draw in the two double bonds. One double bond is always between the two carbons. One double bond is between a carbon and nitrogen. Now, what you do is now you put in the hydrogens. There's always a hydrogen here. And if you notice, it says that this is a base, which means it has to, what do bases do? It accepts protons. It's, the way that I have it drawn, it's going to be this nitrogen here that's going to be the proton acceptor. Histidine is one of the other ones that sometimes they put it in the group of the positively charged amino acids. So if you notice arginine and lysine, which is on the left-hand side, see, they're both already positively charged, where it's really obvious where it can accept the hydrogen. They didn't on this one. So some books actually draw this in looking like this. It's the same thing. It's just that that's where... And it doesn't matter which of the nitrogens you use, because what we're going to find out that's special with histidine is histidine is what they call the great general acid and general base. It flip-flops. Unlike politics, which can be bad for flip-flopping, you would die if your histidines didn't flip-flop. That double bond can swap between nitrogen and nitrogen. So, because it's aromatic, it's delocalized to begin with. And so, but it does that. And so we can have something come in and take one of the hydrogens, like that hydrogen that's on the positively charged nitrogen, come and take that. Or you can have the electron bonds go and smack something else. And so we're going to see lots of things utilize histidine a lot. Because it can be both attacked and do attacking at the same time, essentially, since the two sides can be working simultaneously.
So in histidine, whichever nitrogen is double bonded to that carbon has that plus charge.
Right, whenever it's positive charge. It doesn't always have a positive charge. Like, the way that they have it drawn is also correct. But yeah, whichever one's got the double bond drawn to it is the one that would be the positive charge. Because remember, nitrogen likes to have 5, and that nitrogen we have drawn only owns 4. In reality, that positive charge is being shared between things, so the resonance structure. Right? Then we have, for me, the two that were probably the hardest to ever remember to draw was arginine, which is the guanidino group that you had to memorize, and lysine. I'm going to do lysine first. Notice the one that, for the codes on histidine make sense, HIS and H. Lysine, the code is LYS and K because it cannot be an L because that's leucine. It can't be a Y because that's tyrosine. It can't be an S, an I, an N, or an E. So it's the letter K. But lysine, the hardest part for me was always trying to remember, how many carbons it took between the C alpha and the amino group at the end, and it's 1, 2, 3, 4. So if this is the backbone, we go 1, 2, 3, 4, then the NH3 group, which my 3 ran off. That's a 3. Lysines have very, very special. First of all, it's positively charged most of the time. Not always, but most of the time, under physiological pH. So that means, what can it bind? What are the types of things that it can bind? If it's positively charged, it will bind to negatively charged. What's something in your body you have that's always negatively charged? DNA, right? DNA is a phosphodiester backbone. Your phospholipids, okay? Things like that have lots of phosphates. Lysines like to bind to those, okay? But especially, there are lysine, what they even call them, lysine zippers, which are proteins that have lots of lysines on it that bind to DNA. They even kind of look like zippers. They zip. They bond right along the grooves of DNA. Then we have arginine, and arginine, like I said, it is also the second one that I always thought they were the hardest with those two. And arginine is ARG and R. It can't be A because it's alanine, so they just went with the phonetic one, arginine. And now it has 1, 2, 3. So if we draw our backbone, we go 1, 2, 3. 1, 2, 3. A nitrogen. Oh, I'm going to run out of room again, so I'm going to try to draw it funky. A carbon and a nitrogen. And a nitrogen. And it's almost always positively charged too. It doesn't matter which of the nitrogens that you draw as a double bond, but whatever one you do, like I could have had the double bond going down from there instead of pointing up. But whatever one you do is going to be the one that's going to be positively charged. It's got resonance between those two as well, so that positive charge is shared between those two nitrogens. And it too is important for binding DNA and phosphates and anything that's negatively charged, other proteins making positive. They call them salt bridges because you have a positive charge and a negative charge that comes together to bind. That's an ionic interaction. Arginine is also involved. It's extremely important, one of the major players in one of your metabolic pathways. If someone's already taken them MCAT, you may already know it. Do you know which metabolic pathway it is? It's the urea cycle. Nitrogen fixation, get rid of nitrogen in your body. Okay. It's got some of the most awesome names in that cycle, like argininosuccinase and arginase, which has to do with arginine. But, yep, those are the fun ones. Okay. All right, so at this point, I know it's whatever reason it's going to wait. At this point, I'm going to go ahead and I'm just going to go ahead and end class with prayer.